Now we're going to talk about angular kinematics from this part of the class. And what we're going to do is we're going to start getting a general definition of what it is, and then we'll get into describing human motion with the angular kinematics. How does angular kinematics come into play? Well, as we look at these images here, what we're going to do is we'd probably look at, some people would look at this knee angle. Some people would be like the trail lady angle. And if you look at the runners here on the left or on your right, you can talk about the individual differences in the leg at push-off as well as during motion of the knee or ankle as we're landing. So typically we would not follow the center of mass and use that as a description, but instead we would talk about the different individual joint angles or segment angles and how their running pattern changed. If we can identify their center of mass, then we might use that as a vertical oscillation piece. But generally when we identify running mechanics, we talk a lot more about the joint angles and the segmental angles, which are angular kinematics. In addition, as we talk about the difference in forms of cyclists and what the difference is in a TT bike or a road bike, we can sit there and we draw the individual components of these cyclists with the components of the knee angle at a certain position, or this trunk angle versus the more flat trunk angle of the individual back. So we would say that Andy Potts, which is a lead cyclist, may have a little more trunk inclination or trunk elevation as opposed to the trail runner. And the trail cyclist here, I would say, was be a little bit more aerodynamic because there's less body surface because they're at a greater lean forward. And if you look at the red and the green, that is seen by this white line here. And that would be the trunk angle or trunk inclination angle relative to the right horizontal here. And we can talk about body positioning relative to angles. So just to get a little definition of what angular kinematics is, as it differs from linear kinematics. Remember, linear kinematics is talking about motion moving through, all points move through the same distance in the same amount of time. Where the difference here is we're talking about the same angle of movement during the same period of time. And that's going to be the difference in angular motion versus linear motion. Is during angular motion, it's going to be the same angle at the same time. So they could be, if I have a nice spoke in a wheel, the further I go out in the spoke, there'll be a greater distance of displacement linear-wise. But in angular kinematics, they all go through the same angular displacement. So what is human motion? Well, the idea behind human motion is it's truly going to be general motion, right? And so you've heard me say that before, but motion of the human body is not linear, nor is it strictly angular, but there's a combination of this rotational motion about an axis where all points move together, and then there's also the translation of the center of mass moving or the whole system moving across space linearly. So remember that the motion of human body is a general motion. It is not a linear, purely linear or purely angular motion. It's a combination of general motion. Discussing the different types of angles, we're going to have to become very familiar with two particularly interesting components. And these is going to be relative and angular. Relative and absolute angles. The difference is an absolute angle is also known as a segmental angle. And that think about that as referring to a segment: torso, thigh, shank, foot. So not your traditional what you think of as joints, but more about body segments, and that's why it's called segmental. And there's a couple of key important factors that we need to come into play when we talk about angular kinematics, and that is we need to quickly identify what our reference is. What do I mean by that? Well, we need to identify whether I'm talking about the horizontal or the vertical component of that. And that is, if I do a trunk, and say my trunk is standing up like this, and then it moves more this way. Well, it could be that I went and I increased flexion 4 degrees, or I've reduced my angle by 4 degrees. So I either increased my angle if I had the vertical, or I decrease my angle if it was with reference to the horizontal. Let's see if we can understand a little bit better here in a second. But also I need to identify whether it's the distal or proximal end of the segment. Whether if I'm talking about my thigh, am I talking about the segment that's more proximal and it's closer to my hip, or more distal and closer to my knee? It's very important. I will tell you that traditionally a segmental angle is done from, we call it the right horizontal on the distal end. So the traditional reference for this is the right horizontal in the distal end. So that is your very traditional orientation in reference system with segmental or absolute angles. So to go bring this concept a little further, this is what it looks like. So an absolute angle, here I have the hip. So there's my hip angle, and here's my ankle angle. And again, the references are the thigh is the distal right horizontal, and the angle is that theta right there. And so that's the angle orientation. And you can see this right here, that is represent the leg or the shank. And again, here is the right horizontal, and the angle created is that little area right there. So if you look at that again, you can see that the thigh is from the right horizontal all the way around into where the segment is. And easily, this is, we're not going to do this really right now, but this is the XY coordinate system, and you can use, if you map these right here, to identify what the angle is, because you would create your right triangle, and this one it would be easier to create this right triangle and calculate this angle and subtract 180 and get the thigh angle. So that's why this is on a coordinate system, is because you can calculate from that where you go. Now, in opposition to an absolute angle is what most people refer to when they think about angles, and that's the relative angle or the joint angle. So a joint angle, knee, ankle, hip, shoulder, those are all going to be joint angles. And it's formed by two adjacent segments, right? So the knee angle is composed of the thigh and the shank, or the thigh and the leg, depending on who you talk to. And that's, to calculate that, there's an easy thing to do, right? So we're going to calculate, if you look over on the right again, if you calculate the angle of the thigh and you calculate the angle of the leg, well, it's going to come out to be proximal minus the distal. So proximal is the thigh angle, the leg is the distal angle. So if I calculated the angle of the thigh minus the angle of the leg, that would give me the knee angle, because the angle that's in the middle is a calculation of the proximal minus the distal segment or absolute angle. So that's how we calculate the joint angle. Going forward, this is just kind of it spelled out a little bit more for you, right? So on top here you have your thigh angle, down here you have your shank angle, and this right here is going to be your knee angle. Now it's important that the knee angle that you understand is represented back here. So this is the angle that we talk about with the knee, not this front angle. So it's usually the angle that incorporates where the motion is. So the ankle angle would be this front angle, not the angle in the back. Now, with respect to relative and joint angles, it comes down to where and what reference system you are. Clinically speaking, a fully extended leg produces a 0-degree knee angle. In the biomechanics world, we talk about it as being 180 degrees. And that's because in the clinical world, they talk about degrees of flexed motion. And in our world, we talk about this is the angle at which it is. Okay. So keeping this in mind now we have angular kinematics on top. So again, if you look at this and take a minute and see if you can decide, is A or B representing the relative angle or joint angle? And then also is A or B, which A or B is representing the absolute or segmental angle? And if you said that A is the joint angle or relative angle, you were correct. This is your hip angle, this is your elbow, your knees, right? And so those are all joints or relative angles. And B is all segmental. Now it's very important here, if you look at the motion of this guy, he's going on the page right to left. Excuse me. So what this person has done is created the left horizontal, and they take the angle with which that. Because if I still did the right, that would be a long angle. Okay, so this individual has created a left horizontal for their orientation. So now I hope as you look at this image, which you saw a little earlier, you can get a better idea of how to talk about this person with the joint angles on the back. So if I labeled these A, B, C, D, and E, you should be able to tell me that E has a greater knee flexion in the front or leading leg than D. That means the angle here is less than the angle here, the including angle. All right. Now let's talk about the units of measurement. And this is going to be very important going forward because there are 3 different units of measurement that we can incorporate here. The most common is degrees. Now it's a very arbitrary unit from 0 to 360 degrees. And we'll talk about how you know positive and negative. And then we have radians. Now this is going to be a fundamental ratio. We'll talk about how to calculate what it means, but it's the angle at the center representative of the arc length equal to the radius. You will need to know, and this is going to be a very important concept here, 1 radian equals 57.3 degrees. You're going to need to know this when we convert to the linear application, because we're going to radians. What important thing about radians is they are unitless. And so when we want to convert to the linear world, then we need to put our angle measures in unitless, and it allows the mathematics to happen. If we kept it in degrees, it wouldn't be able to happen, okay? So understand that ratio, it's very important going forward. And then we have revolutions, and 1 revolution is 360 degrees. Now you should also know that a circumference of a circle, right, is 2 pi r, which is 2 pi radians, which is 360 degrees. So this relationship here is where you get the 57.3 degrees from. Okay, just a little backstory on that. But we'll revisit that in a little later time. So when we talk about angular, we're going to talk about this right-hand rule. And the right-hand rule means that you cup the fingers to follow the direction of motion. Okay, and notice these 2 fingers are opposite facing, but that's because one is going clockwise, one's going counterclockwise. Now, for a general rule, when we do angular kinematics, counterclockwise is the positive direction. So unless I tell you otherwise, and the movement that we see is going this direction, it's positive. Therefore, if the movement is going this direction, because that's clockwise, it is negative. That is how you calculate this in a positive and negative world, and we'll talk more about that later. But for this part of the information, know that when you put your fingers in the direction of rotation, this thumb will go in the positive direction of the axis of rotation. So whichever direction that thumb is facing, that is a positive axis of rotation direction. And the size of which that vector comes out, you can see how these are vectors coming out of here, is representative of the speed of motion. See, these are all vectors coming out. These ones don't do anything with magnitude, but in the real world, if you did that, that would be the magnitude of your rotation. Going forward, we need to talk about the position, velocity, acceleration components of angular kinematics. And so we're going to begin, again, of course, with angular position. The abbreviation for angular position is theta, which just stands for degrees, or angle, sorry. Or if you were doing radians, it's just RAD, radians. But you can also get away with just doing theta, not even worried about what the units of measurement are. But again, so here we have, again, if you look at distance and displacement, we have a scalar for distance and a vector for displacement. So if you remember, that vector takes into account magnitude and direction, where scalar is only magnitude. That's the biggest difference between the two, and we have to worry about final and initial, not total path traveled for the displacement. Well, what does that look like? So if we go back and look at the very traditional pendulum concept, and you have, so if I put on this graph here, I have A, B, and C for this. From A to B, the pendulum goes in a counterclockwise motion 70 degrees. So I know that that's 70 degrees, and that's a positive value because it's counterclockwise. And I go from B to C, that is from 70 to 35, but it's in the counterclockwise. So if I do 70 minus 35, that's 35, but it's in the negative direction because it's clockwise in motion. Okay, so if I just did this distance, remember distance is just scalar, so it does not take into account whether I'm going counterclockwise or clockwise. I went from A to B, it's 70, plus from B to C, it's 35. So the total distance traveled is 105 degrees. Okay, but if I was doing displacement, and you can see it down here, it's 35 degrees. Well, how is that 35 degrees? Well, my position final minus my position initial. Position final is 35 degrees positive because I went counterclockwise, and my overall motion minus 0. There I have my 35 degrees. Okay, so the overall path traveled displacement-wise was 35 degrees, but again, if I do it distance-wise, it went ahead and went 105 degrees. Taking it further, we can now move on to angular velocity. Angular velocity is represented by omega, or lowercase w. And again, here we have our rate change. So delta t over angular displacement, which is delta theta. Remember, delta means change of. Your units, we have whatever units you used for your angular measurement, revolutions, degrees, or radians, with respect to whatever your temporal component is, minutes, seconds, hours, milliseconds, whatever it tends to be. Okay, you have the choice and option when you do your measurements to do that. So here we have average omega, or average angular velocity. This sign over the omega is just the average symbol. Here you have your delta position, so your change in position, and your change in time, change in angular position over change in time. How this equation differs from this equation is, again, with the concept of instantaneous. At the ith element, we can figure out what the velocity, the instantaneous velocity is, if we take the ith element plus 1 minus the ith element minus 1. And I got lazy and I just did 2 delta t because we typically only going to do this if we know what the sampling rate is. So what the hertz are, what your sampling rate is, and we can do this. If I didn't know that, then I would do ti plus 1 minus ti minus 1, and that would be my denominator. Going forward, we'll take it to the next level, and we have angular acceleration, known by alpha, and rate change of angular velocity, so delta omega. And again, they're your units of degree measurements or angular position elements with respect to your time squared. We take this all the way down here for the average, and we have delta omega over delta t, and that is your average velocity. Going further, if we want to find out at the ith element, the same concept. Now we have the omegas instead of the thetas. And again, 2 delta t, or ith plus 1 minus ith minus 1. So there, if we don't know what the hertz or sampling rate is, we would put that into the denominator instead. So here we have completed our PVA relationship by integrating the previous to get us the latter. So we integrate position with respect to time to get velocity, velocity with respect to time to get acceleration. So now I want you to practice. Think about this before you go forward. Can you give me a PVA relationship of the knee joint angle with the -1, 141 degrees as the starting position in the downward stroke if we started down, went clockwise, and stopped. Okay, so this is what are some stipulations I want to give you. So a leg, again, we're going to go by my orientation. If it's fully extended, it's 180 degrees. I want you to go 2 full rotations. So that's start at the bottom to the top, all the way around, and do that twice. So you have 2 cycles. And I put this in here for anybody that knows a little bit more about cycling, but these shoes have clips. That means that I can pull up as I push down with the other foot. That means the other foot's not doing all control. So I should have a little bit more velocity going up. Okay, so think about that, and then I'll let you go forward in a second. Also, pause it if you really want to try to do this. But here we go. So we have our PV relationship. I've set this up for you. Here are my units. Remember, some of you missed units. So here are the units: theta, theta per second squared, right? So going all the way down, I have degrees. If I did it in radians, it would be radians per second, or radians per second squared. Okay, so that is the way we set this up, and we have the time on the x-axis. So what do we know? Well, this represents 0, and up here I'm going to put 180. Okay, now if this is the bottom, I would assume probably we don't reach 180. So we're going to say that this part here is probably 90 degrees. And so I know that I start about, we'll say 140. We'll just put this as the 140 spot. Okay. So as I come around, I know my foot is going to end up here. Okay. So the knee is probably going to be out here and out there. Okay. So the angle decreases. Okay, so angle decreases go towards 0. But what I do know is it's not going to hit 0. So what I'm going to say is, again, this is just hypothetical, right? Is here. Then I know that's going to go back up to here because that's where the angle is. But the question is it going to go a little further? And typically it does because of where I started at. So we'll just draw down. Okay, and so I finished where I started. Now again, I drawn this, but so if I looked at this, I would say, just randomly looking at it, that time to complete 1 is here and time to complete 2 is here. So I didn't mean to draw it like this, but I did. So all this is saying is that the time to complete 1 cycle is longer than the time to complete cycle 2, right? So the distance between here and here is greater than the distance from here to here, okay? But let's go through the process now. So now, if you've drawn this and it looks like this, then you're well on your way to understanding what we're doing, right? So from this graph, I say mark this, here, I can mark here, I can mark here, here. So this is an IP, I got another IP, another IP. This is a max, min, and min. Okay, so if you have that concept down, you're with me now. Okay, so if you got those spots, you're going to be with me. Going forward, just draw all your lines down, right? So this is the big process. If you were able to get the position graph, you should be able to follow me all the way down and get the same acceleration graph, okay? So I'd like you to try to complete that acceleration graph if you have time, but that will be how your position graph looks. And you should know from strictly just a sinusoidal path concept that you will kind of shift and maneuver this. But now just think about that and think about what's happening in the gate cycle. And if you can tell me and relate these IPs, min maxes, and what goes with the angular velocity and acceleration all the way down, then you can identify what is going on with the motion of the pedal, how it's speeding up upwards and downwards. Okay, so I look forward to talking more about this, but this is how I want you to continue to develop the connection with angular kinematics. Is if you can create the PVA relationships, what's happening, and identify the different types of joints, segmental versus joint, or absolute versus relative, then we'll succeed and go have a nice job. Thanks.